Okay, let's talk today about section 12.2, comparing two proportions. You should be familiar with tests and intervals of one mean and of two means, and you should be familiar with tests and intervals of one proportion, and today we're going to do two proportions. The test statistic, if you're going to do this test by hand, is, first of all, your hypotheses. Your null hypothesis is always going to be that the two sample proportions are the same. Okay, so you're testing to see, are the samples, what's the evidence for or against the fact that the two proportions are the same. You just assume that they are and then do your work based on that. Your statistic is going to be P1 hat minus P2 hat, or the difference in your two sample proportions, over the square root of P hat Q hat, and again, your book uses 1 minus P hat, I like Q, times 1 over N1, sample size of sample 1, plus 1 over N2. And then one thing you got to know is that this P hat and Q hat here are pooled, meaning that's the combination of all your two separate samples put together to get the complete proportion of successes and failures, P and Q, based on everybody. Um, okay, so that's going to give you your Z value, which you could look up in the old Z chart, the one we always used to figure out your P value in order to reject or not reject your null hypothesis. Okay, so the interval would look like this. P1 minus P2, both hat. That's going to be the difference in the two samples that you selected, plus or minus Z star times the standard error. And the standard error in this case is the square root of P1 hat Q1 hat over N1 plus P2 hat Q2 hat over N2. All right, and all that together will provide you with your Z interval. And again, you should be familiar enough with tests and intervals to know all the basics. The conditions for this are about the same. We need an SRS. We need the population to be at least 10 times as big as the sample. One slight variation, we've tested that NP and NQ both be larger than 10. In this case, you need both of them to be larger than 5 for each sample. So if you read the conditions in your book, it says that N1 P hat, N1 Q hat, N2 P hat, and N2 Q hat are all 5 or more. So you have to get that 10 total, but they both need to be 5. Since we have two samples, that would give you the 10 total. So let's look at an example. All right, here is the setup. There is a new medicine that is supposed to combat this horrible disease of lazy and worthlessness called senioritis. I find 176 seniors and give them the medicine. 156 other seniors, give them placebo, and then I let it work for 2 weeks and see what happens. 144 who had the medicine ended up with senioritis, and 132 did not. Okay, so first of all, let's do a confidence interval. Remember what this confidence interval is giving us. It's giving us a window where we are 95% sure the difference of the two proportions will be. Okay, so I'm just going to do these in the calculator, save some time. With those formulas, you could do them by hand, but I'm going to consider the treatment group to be group 1. So I'm going to go to stat, over to tests, and this is going to be a two-proportion Z interval. All right, and once you choose the right one, the inputs should be very easy. X1 and N1 is how many people had senioritis out of how many people total. So the test group was group 1, the ones that actually got the medicine. That ended up being 144 out of 176. In my other group, I tested 156, and 132 of them got the disease. And I'm going for 95% level and calculate. So what this tells me is that my confidence interval goes from about negative 10% to about positive 5%, which is interesting that this interval goes back and forth across 0. So let's put that into words. I am 95% confident that, now think about what that was a measurement of. That was a measurement of the proportion who had the drug that got the disease minus the proportion who did not have the drug who got the disease. So I'm confident that the difference in proportions for the seniors who got the medicine and the control group is, and then my two numbers were about, let's see, negative 0.1083 and 0.05236. So the fact that this interval went across 0 says that because it's more in the negative side, I'm thinking that my value is negative, meaning the people who got the medicine got the disease at a lesser rate because I subtracted group 2 from that. So if the drug in fact worked, these numbers should be negative. However, if I'm 95% sure, that goes all the way across 0. So as of right now, I'm thinking that it might have worked, but there's part of this interval, about a third of this interval is on the positive side, which would mean that the seniors in fact got it more without this particular drug. The placebo actually did just as well for them. So let's see if we can figure out more with the significance test. Okay, my null hypothesis is that P1 equals P2. My alternative is that the percentage who got the disease with the medicine should be less, which means that P1 would be less than P2. Remember, this is the percentage who got the disease. All right, so this means that the percentage of seniors who took the medicine and got senioritis is less than the percent who got placebo and got senioritis. Sometimes it's good to put your alternate hypothesis into words. So we're just going to kind of breeze through the conditions and assume they are met and go right to the calculation. So back in my calculator, stat test 2 prop z test. And I'm basically putting in the same info. And actually, it carries it over from my interval. I had in group 1, 144 out of 176 got it. In group 2, 132 out of 156 got it. And I'm checking to see if P1 is less than P2, because that would mean that my drug worked. If a smaller percentage who were on the pill got the drug, that would mean it worked. So we calculate, and what do we get? We get start writing down your Z's and your P's for these problems. Let's see, Z is negative 0.6793. So it's down on the negative side, which is good for this medicine. However, the p-value is 0.2484. So what does this mean? This is a high p-value. It's definitely not below 2%, which means that this is not enough evidence to reject the null hypothesis that both percentages are the same. There's a slight decrease, it looks like, in the two proportions, but this is not a decrease that could not commonly happen by chance. If in fact the two percentages are exactly the same, which means that the medicine did nothing, then there's still a 25% chance that we could get this decrease in our percentage. So because p equals 0.2484, I do not reject the null hypothesis. There is not strong evidence that seniors who took the medicine got senioritis at a smaller rate than the control group. There's probably a more elegant way to put that, but that's the point. We do not reject, and I've got my context in there, which means that my medicine hasn't been shown to do any good. All right, maybe it does, maybe it doesn't. We are not accepting that the two percentages are the same, but we do not have numerical evidence to show that it really did any work. So there's your two proportion. This will wrap up our 11 and 12 chapters. We'll start reviewing from here. But I will see you in class. This is Young. I'm your Huckleberry.